So as we move this point, still negative slopes, right? This blue arrow is still a negative slope. So this is a good one to just play around with yourself as you move this and just kind of get the hang of this. But negative, but getting less negative, like right there, it's 0, right? It's a negative slope, but it's heading towards a 0 slope. So negative y value is heading towards a 0 y value. And then now we got positive slopes, positive and getting more positive, boom, 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 right? So understand the f prime graph is a plotting of the slopes of the f graph, right? These y values are the slopes of this graph here. So it's its own function. It's its own function. The derivative graph is its own function. Sometimes we call it the slope function. Okay? All right. Let's go back to this. Maybe I can save that back to what it was. All right. All right. And then, of course, this one we're going to get to later. All right. Back to our thing. Okay. So just quick to review. Question 54 kind of got to this. There was question 20, I think, talked about this a little bit. This was the height of the ball, the velocity. It's just, there's no calculus in this other than understanding that the velocity here, the feet per second, is the derivative of the feet, right? They have the h and h prime relationship. Okay, the feet per second has that rate of change relationship, so it's the derivative. But other than that, it's just plugging in some numbers and so forth. Okay, then we have this speed limit law, and I said, don't memorize this. Just understand it says if they tell you something about the slope, if they tell you something about the rate, then that tells you something about how far you traveled or how much the graph goes up or down. Okay, if you know something about the slope, you know something about the steepness of the graph and how far it goes, and there's some problems on that as well. Okay, and then of course we said f prime is the instantaneous rate of change or the slopes of f, either one, depending on what kind of problem you're dealing with. Okay, what are some ones you had questions on? Here, let me talk about this real quick, and then we'll see if you guys got something you want to do, because this is so critical. I'm going to just pick out some that I want to make sure we go over. If you've got some others, we can talk about it, but these are the main ones. So here's an F graph. So this is 14 and 15, I think. So here's an F graph, and they want to know the slope at -2. Now, this is, one of the things you'll have to do on the next quiz is you'll have to do some slope calculating, right? You're going to have to do some, calculate some slopes. Now, at this point in time, until we get to chapter 2, the best we're going to be able to do is estimate slopes, right? So notice I said approximately. The best we can do is estimate these slopes, because can you do the slope at one point? We did that the first day. Now, one thing about your book is they don't know that we already did this, so in your book's mind, this is the first time you're seeing some of this stuff. But we already talked about that. You can't do slope at one point. You need 2 points, right? So right now, when we want to find the slope at -2, we really can't do that. Okay, if all we have is this F graph. But what we can do is we can sketch in a little tangent line here, and I like to make it as long as I can because I'd like to go over 1 if I can. So I'm going to go over 1, and how far up do I go? 10? Yeah, mine did go up 10, but I don't think I drew mine very straight. It probably should have went up higher. So it looks to me like if I go over 1, this line goes up 10. So I'd say that slope's about 10. I'd say that's pretty good. Now, what am I going to do on the quiz? I'm going to look at your tangent line. I'm going to expect that you drew in a tangent line. I'm going to look at it. I'm going to check your rise and run. If you just have an answer here of like 7, and I don't think that's very close to the right answer, unless I can and you don't have a line, you're probably going to miss points. But if I can see your line and I can see you kind of angled it and you didn't draw it very straight, I don't expect you to get out a ruler or anything, and I can see you went up 1 or you went over 1 and up about 7, then I'd probably say, okay, you're good. I can see your line wasn't very good. Now, if you draw your line like this, now you're going to miss it because that's really bad. Okay, that's not even a tangent line, right? So it's got to be something reasonable. Okay, all right. So and then it's 0. And then that's this one right here. So if you go through here like this, oops, that's bad. If you, this is almost a line as it goes through here. So it looks to me like we go over 1, it goes down about 6 maybe, -6, somewhere in that ballpark probably for that one, for 14 and 15. Okay? All right. Now I'm jumping to 25. And now again, when we get through this, if there are some that I haven't went over that you are bothered by, then we could, if we have time, we could take a look at it. Okay, this is the classic speed limit law problem. All right, so as soon as you see this right here, what comes to mind? If h of 0 equals 0, what's that make you think of? It's a point, right? That's what you should think. That's how we're going to give points in this class, right? It's going to be this. It's going to be h of 0 equals 0. So I'm going to draw a graph. I mean, not always, but a lot of times, if they give me a point, I'm going to be like, well, let's draw a picture of that. Let's plot that point, okay? And then what does this mean? The slope is less than -2. What's that mean? So that's good. That's how I want you to read that.
So it's going to be -2 until I go -2 or less.
So what's -2 or less mean? Never going to go up. Okay, there's the key word right there. I think it's over 1. To me, when I hear about slope being less than or equal to -2, to me, I think that means if I go over 1, I can go down 2 or down. No, I don't think I can go down 1. It says less. What numbers are less than -2? -3, -4. See, you're thinking steepness, right? No, what numbers are less than or equal to -2? -3, -4, -5. So that means if I go down 1, I can go down 2, but I could go down 3, I could go down 4, I could go down 5. Like Max said, you can't go up. Not only can you not go up, but you can't even go down just 1, right? You got to go down 2 or more, right? That's what you want to think of. The slope is less than or equal to -2 means if I go over 1, I got to go down 2 or more. Well, then they ask me this question. Well, what's h of 5 then? Where is h of 5? Well, okay, forget this though. I mean, just, what are they telling me? Think about the language I was just using. If I go over 5, right? Because right now I'm here. So they're talking about h of 5. Forget the -10 for a minute. They're just saying the output value at 5. Well, how do I get to 5? I got to go over 5, right? From 0. So what did we just say about the slope? If I go over 5, what do I got to do? I got to go down 2 for each one I go over, so I got to go down 10, right? Now this is how I would explain this, and if this question's on the quiz, which is very likely that there'll be something like this, then I would have a picture like this, and then I would say, since the slope is -2 or -3 or -4, ... if I go over 5, I have to go down at least 10, maybe more. So therefore, h of 5 has to be less than or equal to -10, right? Now, I'm not saying you have to have all of that, but more is better, and a better explanation is a better chance of getting full value on your points, right? Don't make me guess at what you were trying to say, okay?
So you can only go down 10 first?
No. It's saying that's the least you can go down, because remember, what did we say the slope is? Slope is less than or equal to -2, which means it could be -3, -4, -5. So I could go over 5 and down 10. I could go over 5 and down 15. I could go over 5 and down 20, right? That'd be if the slope's -4, right? So it's got to go down at least -10, but it could go down more, right? So that means my y value, because that's what h of 5 means, the y value at an x value of 5, the y value has to be -10 or lower, less than. Okay, then it says, now it asks it different. It says, one says, what did it say? One says is or explain or show that, and the other one it says explain why this must be true. Basically the same question. So what about this one? And sometimes I might just say true or false, right? I might just say, could h of 3 equal 5, for example? Right, I might say, or something like that. But in this case, is it true that h of 3 is less than or equal to 5? True or false? Emily, true or false? We talked about this one, didn't we? We talked about this one.
It has to be -6.
So, Will, is that why you're saying false?
Yeah.
Max, what'd you say?
Okay.
Right. But it says less than or equal to 5. Right?
It's true, but like -6 is
That's right. So this is true. This is true. If you go over 3, where do you got to go?
at least that is.
You have to go down at least here. So the values that h of 3 could be would be these red values, right? The red h of 3 can be any of those red values because it's got to go down at least 6, but it might go down more. So h of 3 has got to be any of those. So is it true to say that h of 3 is less than or equal to 5? Sure. It's less than or equal to 7. It's less than or equal to 100. Like and I know you said what can't be equal to, but it's still okay. Like for example, would it be okay for me to say, okay guys, you don't know how much money I got in my pocket, but I got less than or equal to $1 million in my pocket. That is a true statement. Trust me. I have less than or equal to $1 million in my pocket. Right now. Okay? So, yeah, it's an or, right? So is h of 3 less than or equal to 5? Most certainly it is. Not only that, it's less than or equal to -6 is what it is, right? That's the cutoff, but it would be true to say those other things. Sometimes they say, find a number L. We had a question in one of our earlier homework assignments. Find a number L such that, or did they do that in one of your other problems? No, they didn't. Find a number L such that h of x, or h of 3 is less than or equal to L. So what number would they be looking for L? The -6, right? But couldn't 5 work, right? Well, no, it couldn't, because then if you say, well, h of 3 is just less than or equal to 5, that's not true, right? See the difference in that? Because if they say find a number L such that h of x will be less than or equal to L, you say, well, less than or equal to 5. No, because then that's like saying it could be 4, it could be 3, right? But they're asking a different question there. They're just saying, is it true that h of 3 is less than or equal to 5? Most certainly, because it's -6 or less. Okay, and then it says talk about it in car talk. So this is a great question too. These are the kind of things I'm going to want you to be able to do on this next quiz. You're going to definitely have to interpret these things, what they mean. You're going to have to show an understanding of this concept we're getting at here. Okay, now we got a number of days to keep working on it. But car talk. So now, so we got to put some units on this, okay? So let's put some units. Well, if it's a car, miles per hour, probably the best unit. So that means hours would go here. That would mean what would be the units here? Miles, right? And then the slope would be miles per hour. So what would this be telling me here in the car situation? That's Bismarck, right? That's my starting point. We'll say we're at Bismarck. What's this say? Going west, 2 miles per hour, right? Because it's negative. So h prime is miles per hour. Right? H is miles. We said the derivative is always these units over these units, right? Because it's a slope. It's rise over run, right? Y is over x. So the slope, miles per hour. So this is, we're going to go west at 2 miles per hour. So what is this one saying? No, not 5 miles. That's the input. That's the x. That's hours, right? At 5 hours, you have to be 10 miles west. Doesn't that make sense? If we start at Bismarck and we go 2 miles an hour to the west, after 5 hours, we have to be at least 10 miles to the west. But we could be farther, right? Because we could be going 3 miles an hour west or 4 miles an hour west, right? What's this one say?
3 hours.
After 3 hours, what's the 5 mean? 5 miles east, but what's less than 5 miles east mean? Here's 5 miles east. So less than 5 miles east means you give me a direction. West of, so if I'm not 5 miles east, right, not quite 5 miles east, that means I have to be west of 5 miles east, right? So after 3 hours, this is saying you have to be west of 5 miles east. Wasn't that true? Yeah, not only that, we have to be where?
6 miles.
We have to be 6 miles west, right? Because remember, we're going 2 miles an hour to the west. So after 3 hours, we have to be 6 miles an hour west. Is that west of 5 miles east? Okay. Definitely. Right? I mean, You got to think about you got to slow down and just think about what each one of those things is. Okay, 28, another speed limit law. I think this is important, so let's talk about it. So here we got f of 0 equals 2. So that means we're starting here. If f prime is greater than or equal to 4 all the time, that means what? Slope is 4 or more. It could be 5, could be 6. That means you go over 1, you're going to go up at least 4, right? So they say, what's a possible value of f of 1? Well, that means if you go over 1, you have to go up how far? So where are you at? No, not greater than or equal to 4. 6, because you were at 2, right? You were at 2 and you go up 4, so you have to be, f of 1 has to be greater than or equal to 6. Has to be, because you have to go up at least 4. And again, this picture with some words is what you'd want to have there. Okay, then they ask you about -3. Well, if you go over 1 and up 4, what do you do if you go backwards? You go down 4, so that would put you at what, -2? And then another one would put you at -6, and another one would put you at -10. Now the question is, so here's -10. So the question is, are you down here or are you up here? Where, I mean, it didn't say it equaled 4. So if it equaled 4, you'd be right here. It said the slope was greater than or equal to 4. So what other y values could we have? Doesn't have to be down here. Because the slope could be 5 or 6, which means steeper. So if the line goes through here and it's exactly 4, it would hit here. But if it's steeper than that, it would come down like this, right? So if it's steeper than 4, so it could be anything below -10.
So does that mean the point the slope's the same for every point?
No, that's the whole key. If it said f prime equaled 4, then yeah, the slopes are the same and you'd have a line, right? That's what a line is. The slopes are the same all the time. We're saying that we know this graph goes through here and we know the slopes are always 4 or more. So that means they're always steeper. So yeah, chances are it doesn't go right through here. About the only way it could is if it's a lump. So it's probably curving, so but it's always steeper than 4, right? It's always steeper than 4. So that's why we have less than and greater than in here, is it's not the same all the time. So that's why we have a range of answers. F of -3 could be anywhere 10 or below. All right, let's talk about these graphs. Okay, position, velocity, acceleration. Now it's important to understand this because here is an idea that V here is the same as P what? P prime. And acceleration is the same as V prime. That's right. It is the slopes, and what the heck, we might as well introduce a new notation today. It's the same as P double prime. In other words, the derivative of P is V, that's P prime, but if you want to do the derivative of P prime, just think about it. P prime is its own graph. It has slopes. So you're talking about the slopes of the slope graph. The derivative of the derivative. So if you do the derivative of P prime, that's P double prime. Simple, right? It's just the slopes of that graph. Okay, and you can have triple prime, we don't. We typically have P prime, P double prime, and that's as far as we go. There's only one example of any time we ever need a third derivative. Okay, so we typically call this the first derivative, the second derivative. A lot of times we'll just call that the derivative, but the first derivative. But if we have double prime, we'll call that the second derivative. Okay, but this is a really important thing to understand. So we're talking about a car, we're just talking about an object. It doesn't really give you any units. Let's use miles per hour. So this would be miles, this would be hours. What would be the units on V then? Miles per hour, and this would still be hours. And then what would P double prime or V prime be? Miles per hour squared or miles per hour, right? And this again is still hours, okay? So 32, they say the object moves away from the origin, like Bismarck would be the origin, at a constant velocity. So you're gonna have to start here and the graph's gonna do what? Okay. All lines are straight. So you don't have to say straight line, right? Because if it's not straight, it's not a line. But I know what you mean, right? But you don't mean horizontal, do you? How about diagonal? That'd be a good one. And goes up or down. Does it have to be up? Positive X. That's why I haven't drawn a negative X over here. So we're going this way. So we're starting at noon like Bismarck and we're going that way, right? So that's positive X. But if I draw it up, that means I'm going which way from Bismarck? East. Did it say anything about how you had to go east? It just said you're moving away from the origin. So couldn't I draw this going down?
Couldn't they make plus possible?
Yes, we could, right? And usually you would, but we're going to do this. If it's not defined, then right is always positive and left is always negative, and up is positive and down is negative, unless we're told different, right? So that way east would always be positive because it's to the right, okay? But you're right. I mean, if we defined them the other way, then we would go with that. But my point is this. You have more than one right answer for these problems because they didn't tell you, right? So let me draw this one, but it would have been okay to draw this one. The red would have been okay too. It just has to move away. Now, why does it have to be a line? Because it's constant velocity. If it was curving, then your velocity would be changing, right? Because the velocity is what on this graph? No. What is the velocity on this graph? The slope, right? This is what we're talking about. This is what derivative is, right? It's the rate of change. The slope of this graph, and this is how you make these graphs a lot easier to draw. If you think of it as slopes, the slope of this graph is the velocity. So if they say we have a constant velocity, we have to have a constant slope. So we have to have a slope of 2, 2, 2, 2, 2, 2. Well, that's a line. Or we can have a slope of -2, -2. That's a line. Okay, now, if you think of it in those terms, this graph becomes a lot easier to draw. So my blue graph, what would it look like? Horizontal line where? The blue one. We're doing the blue one.
If it's 2, then it's at 2.
It's got to be up above, doesn't it? Because the blue line has what kind of slope? Positive slope. So if it's 2, so remember what I said? The derivative graph is a plotting of the slopes of the original. So slope 2, slope 2, slope 2, slope 2, slope 2. Y value 2, Y value 2, Y value 2, Y value 2. Right? And the red one would be where? Down here. Right? If I wanted to do that one. Okay, what's the acceleration graph then? What do you mean at 0? Right there. Where would the red one be? See, people get all freaked out. Acceleration. Well, I don't know how to graph acceleration. Don't think of it like that. What are you graphing right here? You want these y values to be what? The slopes of this one, right? What's the slope right there? 0, 0, 0, 0. So let's plot that value. 0, 0, 0, 0, 0. Okay. 35 says the object is moving back. Is that right? 35 says the object's moving back towards the origin. Now, people get confused because they think this is the origin. That's not what we mean. We mean Bismarck's the origin, right? Bismarck's the origin. What's that? That's 37. What's 35 say? Moves to the right and then to the left. So here's Bismarck. Now, does it tell you where it starts? Does it have to start right at Bismarck at 0? It didn't say that, but did you assume it probably did? I'm guessing most of you probably assumed it did. So so let's say we started it there, but what we had? Could we have started it up here? Right? It could have started over here east of Bismarck and then went to the right and then back to the left, right? Okay? But let's say it started at 0. That's fine. And so where's my graph got to go? It's got to go up. Now, does it have to be a line? What would make it have to be a line? Constant velocity. They didn't say that, did they? So, how many of you drew something that looked like a V like that? That'd be reasonable, because we just got done doing that one on 32. But couldn't it have done this? Couldn't it have been a parabola? Couldn't it have done that? Now, let me just, for ease sake, let me make it come right back to there. Same answer. Couldn't it have been curved?
Does that mean that it's going north of?
No. Don't confuse. We're just talking east and west here. We're just talking east.
Like west would be the negative.
No, east is positive.
And then how do you?
Think of it this way, Emily. Think of points. This would be the point 0, 0. So that means at 0 hours, it's 0 miles. So it's right at Bismarck. Okay? Now think of this point right here. Think of that point as 1 and 15. Right? Whatever. So that means after 1 hour, it's where? 15 miles. That's positive, so that means east. So it's 15 miles east. And then think of this point as 2 and, 30, whatever. So now 2 hours, it's 30 miles, right? But then it gets to here, maybe that's at 50. It's now 50 miles east. Well, now here, what's happened? Now it's only 30 miles. Now that's only a y value of 30. So that means it was out here 50 miles east, but now what? Now it's coming back. Now it's only 30 miles east. See how that's coming back? So it went to the right, then to the left. Okay? All right. So that is, either one of those could have been your graph, because it didn't say what the velocity was. But isn't that going to change your next graph depending which one of those you did? Right? Because what is the blue graph going to look like now if you go over here to do the slopes? It's what? It's not going to be curved. What's this part going to look like? Yeah, what's this slope? Just give me a guess. What's the slope right here? 3. What's the slope right here? 3. Well, yeah, if that first one is 3, it's got to be 3. It's a line, right? What's this slope? 3, 3, 3. So let's plot that. 3, 3, 3, 3, 3. Right? It's got to go like that until here. Now what's the slope? -3. -3, -3, -3, -3. So let's plot that. -3, -3, -3, -3, -3. That's what your graph would have to look like if you were doing the other one. Now, which one of those, the red or the blue, is more realistic in real life if this was a car? Isn't it the red one? I mean, because what would have to happen? This car would have to be, as soon as it starts, it's going, whatever, 3 miles an hour. And then what happens right here?
Stops, it goes.
Instantly changes from 3 miles an hour this way to 3 miles an hour this way, right? That ain't going to happen, right? So this is not a very realistic situation, right? That the velocity is 3 and then instantly changes to -3. It's more likely to be the red scenario. Now, what would the graph of the red look like? So now, give me an example of what the slope is right here. This is how you graph this, because what are we trying to do over here? We're trying to plot the slopes of this graph. So let's get some numbers in our head so we can plot them. So give me a slope right here. No, you just told me this was 3. You just told me this was 3 and this is up higher. Doesn't it have to be steeper? Jeez. 5. What about here?
6.
No.
4.
No, but this is key. This is really critical. What are these slopes doing? They're getting less because it's what? Why? What's the word? We've used it already. Curving. What do we call this when the graph does this? Concave down. Since it's concave down, those slopes are getting less, right? 6, 5, 4. If they were getting steeper, we'd have concave up, right? That's going to be really critical this week. And we haven't talked much about concave up and down right now. But that's what it is. So, okay, back to this. So, slope of 6, then 5, then 4, then 3, because we're headed towards a slope of 0, right? So let's plot those. Now we said this was 3, right? So we better start up here. We said 6, right? We had 6, then 5, then 4, then 3, then 2, then 1, heading towards a slope of 0 right there at that same peak, right? Then what are the slopes? -1, -2, -3, getting steeper, right? So -3, -4, -5. So here we go, -1, -2, -3, -4, -5, -6. This would be. Now, do we know it's a line? Do we know it was exactly going down in those even increments? No, right? This could actually curve. All we really know is that it's going down. It couldn't curve up and down. It would have to go down, but it could be kind of an S shape. It could kind of come down and then kind of go here, right? We don't really know because we don't know how those slopes are changing. But let's say we made it a line, okay? Now, let's go to the blue graph. What would the blue graph slopes look like? 0 and then still 0. So we would just have this graph again. What would the red graph be? Well, it'd be the slope of it. What's the slope right here? I don't know, but what do you just give me a number? 4. -4, thank you. -4, -4, -4, -4, -4, -4, -4, right? So how would I graph that? Horizontal line, but down here. Okay, 37. This is the one where it's moving back towards the origin. Does it say it was an east or west, or it doesn't say anything? It just says the object's moving back towards the origin. Now, by origin, we don't mean this point. That's the time. We mean Bismarck, right? So we got to be somewhere. Let's say we're east. Let's say we're east of Bismarck, and we're going to come back towards the origin. So where do I start my graph here? Up here in the positive, right? I'm like 50 miles east of Bismarck, right? So at time 0, I'm at 50. And I'm going to come back towards the origin. So where do I go from here? Just going down, right? Now, do we go past the origin and keep going? It doesn't really say, does it? Okay, so if we want to just draw a line, back to the origin, right? By origin, we mean our starting point of distance. We're back to 0 miles away. So what we get to the x-axis. Now, I could have curved that. So I could have had it do this. It could have come down kind of like a parabola. I could have curved it. Now that's going to affect the slopes, right? So if I would have made a straight line, then what kind of graph would I have over here? Horizontal. What's the slope? -2, -2, -2, -2, -2. That'd be down here. Horizontal. What would be the slope? What would be the acceleration over here? 0. But if it was the red graph, give me a slope. What do you think the slope is right here at the beginning? Depends how I drew it, but if it was the peak like of a parabola, it'd be 0, wouldn't it? So you could reason that my slope starts out at 0, then what? -1, -2, -3, -4. So you could say starts out at 0 and then -1, -2, -3, right? These are the y values, right? These y values are the slopes over here, right? The slopes here are the y values I'm plotting here. And if that was the case, what's the slope of this? If it's a line, let's assume. What might this slope be here? -3. -3. -3. If it's a line, it's -3 the whole time. So then that graph would be down there. Oh, darn it. Why didn't somebody tell me that? Okay. At a steadily what? At a steadily increasing speed. So which one would be right, the blue or the red? The red would be the one. It's getting steeper, right? It's going back towards the origin. We start at 0, then -1, -2, -3. So it's increasing speed, getting faster and faster. So forget the blue graph there. Should have been the red. Now, and it said steadily increasing. So that tells me that this would be a line, right? Because it's steadily getting steeper and steeper. So that means at a constant rate, so then that red one would be aligned there.
So how come that doesn't have a constant, like, slope and that one, then the velocity does? Like, how come that is,
Well, because they're two different things. This is steadily increasing speed. So this starts out with a speed of 0. We're talking about slope now, right? Because that means it starts out 50 miles. Then after an hour, it went, it's at 40. So it only went 10 miles. But now in the next hour, it's going to go faster because it's going down steeper, right? So it's going faster and faster. Well, what we're graphing, remember, this is the key element, Emily, to remember, is you're taking these slopes and you're plotting them over here. So if this is a slope of 0, then we plot a 0. If this is a slope of -1, we plot a -1. Then if this is a slope of -2, you see how it's getting steeper? The slopes are changing. So are these y values are changing. But see, you can't talk about the slopes of this one and compare it to the slopes of this one. That's not what we're saying. The slopes of this one are the y values of this one, right? So if these slopes aren't changing, which is true on a line, then that means these y values can't change. Well, if the y values can't change, then it's horizontal, right? You can't compare the slopes of this one to the slopes of that one, because that's not what they're saying.
Is there a direct relationship between P and A?
Well, right. It's this relationship right here. It's that A is equal to P double prime. I mean, that's the direct relationship.
A is the slopes of the slope of B.
Yeah, I mean, yeah. So in a sense, not really. Although, yes, there's going to be, if you know double prime, it tells you right away something about A. But we're going to get to that later.
Is there like any way that A can be curved?
Sure. If we would have, remember we said here they didn't tell us anything about the steadily or whatever. So if we'd have drawn a red one like this, curve and then curve, kind of an S curve, then all of a sudden the red one would now be curved. Or it would at least not be horizontal. But yeah, because then we could say, well, these slopes are negative and getting more negative, so this slope could be negative and getting more negative, and we could even curve it, whatever, like so. Yeah, absolutely. All right, 41, we got to rock. Well, this is really important, and there's not a whole lot new in section 5, so we're not going to spend a lot of time on that anyway. But let's talk about 41. That's a really key problem as well. Guaranteed on the next quiz. Here's one of those things where I'm telling you. Guaranteed on the next quiz, you're going to have to do this on 41. You're going to have to interpret what a function means. You're going to be given the units, just like we were talking about car talk, miles per hour and that kind of stuff. You're going to have to be able to interpret this in terms of the language. Now, you're given that H is what? What units are H? Hours, let's be more specific. So we just went through daylight saving time, right? Change. Okay, so this is a good problem to talk about. The hours between, what would be a shorter way of saying it? Hours of daylight. Isn't that what they're saying? The hours between sunrise and sunset. So we're talking about hours of daylight. Okay, so the hours of daylight. Now, at daylight savings time, that didn't really change, right? We still have the same hours of daylight. They just happen earlier in the day, right? So it's a little lighter when you go to school. Okay? But it's going to be darker earlier at night. Okay? So the hours of daylight, and then over here are the days after January 1st. Right? So what would be, right? So the very first thing you should do when you see, okay, they talk about H prime is think to yourself, what are the units of H prime? Yes, hours of daylight per day. It's the change. It's a rate of change. It's a change in the hours of daylight per day. Don't we have that happening right now? Well, it happens all year long, but a lot of times you don't notice it. Aren't the hours of daylight changing? They're getting what? The days are getting shorter. We're having less hours of daylight in each day right now. Up until when? What's the shortest day? The winter solstice, which is December 21st, right? So the days are getting shorter. And then after that, then they'll start getting longer again. Okay? And you don't notice it so much here, probably in the next few weeks. You'll notice it because we just went to daylight saving time. But as you get towards it, well, we'll talk about this a little bit here in a second. But that's the first thing you need to do is figure out that H prime units, so these units right here are going to be hours of daylight per day. So, what are these units right here? The 100. Days after January 1st. Okay, so now tell me what this says. Somebody volunteer. You got it? Go.
100 days after January 1st. It's gonna be 0.05 hours.
Now, who would talk like that? 0.05 hours. Let's put that into something reasonable. Get your calculators and put that into something reasonable. Nobody talks like that. 0.05 hours.
It's not very much daylight.
That's not very much change, is it? Right? And we're not saying that's how much daylight there is. That's the rate of change. What? No, it's 0.05 hours. What is 0.05 hours?
Oh, minutes.
Well, that would be better, right? I mean, 0.05 hours is a small unit of time, so I would think minutes would be better. Yeah, I wouldn't change it to months or weeks, I don't think. That would just be worse. That'd be 0.000 something, right? I'm purposely not telling you. I want you to think it's Monday morning.
3 minutes.
3 minutes, 0.05 times 60, right?
Wait, can you do that? Can you change the...
Sure,
Be changing like...
absolutely, absolutely. 0.05 hours is exactly the same thing as 3 minutes, right? So, okay, so say it again.
So 100 days after January 1st, there is 3 minutes of... Is that daylight per day? Actually...
Well, you wouldn't want to say there is 3 minutes of daylight per day.
It's going more than daylight.
Why more?
Because it's
Because it's positive, and if you're going to say more than, you better say more than what?
You just said that it's increasing.
Increasing, okay? There'd be several ways you could say this. Now, I'd like for you to say it in a way that would make sense and like normal people would talk. But if you want to do it just a purely mathematical way, you would say this. I like better than 100 days after January 1st, I'd like to say on the 100th day after January 1st. And even better yet would be to count 100 days after January 1st and give me actual days, right? That'd be about 3 months plus 10 days. So January, let's assume they have 30, January, February, March, we'd be into April. About April 10th would be reasonable. Okay, now it'd be better to find the exact date, but right, okay. But let's say on the 100th day after January 1st, the hours of daylight are increasing, right, by 3 minutes per day. It's April 8th. Okay, on April 8th, the hours of daylight are increasing by 3 minutes per day. That would be a great answer. Now, you said more than, because that's the same as increasing. You could say that on the 100th day, or on April 8th, there are 3 more minutes of daylight than, no, not January 1st, April 7th. It's per day. It's per day. So if at that instant, it's not every day it's increasing by 3 minutes per day, just on that day, right? Because this is curved. This isn't a linear thing, right? Some days it's going faster. Matter of fact, we're going to talk about that in a second. There's some times of the year where the hours of daylight is changing faster than some other times, right? Now, it turns out that this is a pretty fast time. In April, that's a fairly fast, the days are getting longer. That's in the spring, right? Aren't the days getting longer in the spring? What's the longest day of the year? June 21st, the summer solstice, right? So in April, the days are getting longer. And at a pretty fast clip, right? That's when it's starting to warm up, right? And the days are getting fast. So 3 minutes per day is a pretty good increase. Okay? Now the days are getting shorter, but it isn't by 3 minutes per day. It isn't quite that fast right now, probably. Okay? Those would be the kind of answers you'd want. On the 100th day, it's increasing by 3 minutes more than the 99th day. Okay? That's what you'd want to say. I like increasing. Now, if this was negative, then we'd say decreasing. Now, don't say decreasing by negative 3 minutes per day. Now you've done a double negative, right? Don't say decreasing and then say negative. If you want to say changing at negative 3 minutes per day, that's okay, right? All right. Now, when is H prime less than 0? In other words, when would it be, that's the other part of the question, when would it be negative?
It's decreasing.
After June 21st, right? Whatever day that would be, right? Because that's when it would be decreasing the minutes per day. Now, this always interests me, and so I'm going to make you guys be interested too. So you guys are sitting here facing to the east. One nice thing about this new school, it's the same as my old one, because I always use this example, and my old one faced to the east also. So we're facing east, okay? So let's imagine this, we're facing east, south is over here to our right, so we're facing east. Now, as the sun comes up in the morning, right? It's in the sky, but it is not directly straight to the east. Where is it? No? It's a little more southeast. Why? Why? Yeah. Where's the United States on the globe? In the northern hemisphere, right? We're in the northern hemisphere. So when we look to the east, the sun is a little bit to our south. Okay, because the equator's down there, right? Okay. So the sun rises in the morning, let's say it's about here, okay? And it's coming, I'm saying it's coming overhead. So we would look a little bit to our south and we'd see the sun coming overhead, right? Now, when is it high in the sky compared to more down here? When is it farthest over here? In the short days. In the winter, if you pay attention, the sun is lower in the southern sky as it goes across on the shorter days. In the summer, it's higher in the sky, right? So if you think of it this way, think of, as the year goes along, think of the summer solstice as when the sun is up here high. And then as you go day by day by day, if you came out at noon every day and looked, right? Starting June 21st, you'd see the sun here, and then you'd see it here, and here, and here, and here, right? All the way until when? December 21st would be the lowest. And then what would happen? Start coming back up. So if you graph that, you'd have something that look like that, right? Okay, so I want to look at that. So this would be June 21st, and then this would be, right, December 21st. Okay, now, here's what you would have. You would have, so right now we're where? We're over here somewhere, right? We're over here somewhere. Now, so what we have is that sun. So we can imagine like a time-lapse thing, right? We have that sun going down, 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 down. Now it's slowing down, right? It's slowing down because our minutes per day are not changing that much right now, okay? So, boom, it's about the same, slow, 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 slow. Think of the ball and the metronome. Throw it up in the air. What happens? In the beginning, it's going pretty fast. What happens to that ball? Slowing down, slowing down, slowing down, gets to the top, stops, comes back down kind of slow, but then it starts speeding up, speeding up, speeding up, right? Think of that same thing here. So right now, we're down here somewhere, slowing down, slowing down, slowing down, slowing down. We get to December 21st, what happens? Well, no. Stops. Then what? Starts coming back, but fast or slow? Slow. So in January, the days are still short. They're getting a little longer, but pretty slow, right? You don't notice much difference. Okay, so January, now you're getting into February, right? And then you get into March, and then what's March 21st? The spring, that's your birthday? The spring starts with an E. The spring equinox. The spring equinox. Now, what's equinox mean? It comes from equal. No, that's not changing. The day and night are the same. That's right. You have exactly 12 hours of daylight and 12 hours of darkness. That is right here in the middle. But what about the speed of the sun moving across the sky like that, about your minutes of daylight? That's the fastest. That's like your inflection point. Right? Now on March 21st, that's when the days are getting longer at their fastest rate. Okay? Now, comes across and it goes boom, 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 boom. Now it starts slowing down, right? You get into May. Now the days are pretty long. You get out of school in late May. Get into June. You really don't notice the difference, right? It gets dark about 9 o'clock. About the same, right? Because it's going pretty slow. It's going pretty slow. Now it gets to here. Now we call that the solstice. What's the word solstice come from? What's that mean? What did we just say happens? The sun is like getting higher and higher in the sky. It hits here, and what's it do? Stops. You know what solstice? You know what sol mean? S-O-L. Sol is sun. Solstice means when the sun stands still. That's what that comes from. So that's when it's moved, it's coming up, getting higher and higher in the sky, and then it stops. And then it's going to go back. Right? There you go. If you didn't learn any calculus today, you learned a little bit of that. Okay? All right. So that's a good scenario. Now, what would the graph of this look like? If you said, here's your number of days, so let's say we start pretty short right now at January 1st, because that's almost the shortest day of the year, right? It's not quite, so it wouldn't be the bottom. December 21st would be back here, so this would be your shortest day. But it'd be coming up, and let's say your longest day is maybe close to 15 hours. Let's say that's in the middle here, right about in June, or close to the middle. It would come up and look like this, and then it would come back down, and then on January 1st, we'd be past our middle. Actually, it would lower, and it'd be on its way up again a little bit on January 1st. Then would you imagine it'd be kind of like a sine curve kind of a thing? That's exactly what it is. And guess what happens right in here is March. That's when it's inflection point. Then it's kind of slowing down, and you get your longest day, and it's kind of slow, and then it's getting shorter and shorter days. September 21st is the fall equinox, right? That's your inflection point right here, getting short pretty fast. And then now we're into this where it's going to get the shortest. So it's kind of it's a sine curve kind of a thing. All right, 42. So you were supposed to rank these in order. So all you had to do there, I'm going to rank these in order. F prime and -3. So here's -3 right here, kind of do the slope. It looks like it's about 0. Okay. F prime and -2. What's that slope look like? Well, if I draw a line in there, if I go over 1, it looks like each one of these is 1. Looks like if I go over 1, I go up about 1. So that's a 1. What's F prime is 0? F prime is 0 would be right here. If I draw a line in here, this is all I wanted you to do. You go over 1, it looks like you go up what? 1, 2, I'd say it's a little steeper than that. I'd say it's about 3. Okay, that's the next one. F prime of 1. Drawing that line. Looks to me like if I go over 1, I go down 0.8 maybe. I don't know. Down 0.8. I'm doing this pretty quickly, but F prime of 4 would be this slope right here. So that looks to me like if I go over 1, that's at about 1/2. I go down about 1. I don't know. Those two look pretty close to me. I don't know. In increasing order. So this one would have been the least. So F prime of 4 would have been the least. F prime of 1 would have been next least. Oops, F prime of 1. Then this one, F prime of -3 was about 0, and then this one was about 1, so that'd be F prime at 0, and then what was this one? 3. Oh no, that was F prime of 0. This was F prime of -2, wasn't it? F prime of -2, and then the biggest one looks like it was at F prime of 0. So just put them in order, right? Just rank them. So that this is mostly what we're going to be talking about today in section 1.5 is just simply finding these slope values. One way to do it on a graph is just to sketch yourself a tangent line, do a rise over run. Do a rise over run. Okay? 47. This is really an important one here. 47, and they want to write the equation of the tangent line. Remember, the equation of a tangent line is your slope, x minus your point, plus your other point. Well, they give you the 0.15, so that's easy. You got 1 and a 5. All you need is a slope. You need F prime. Here's the first time we're using this notation in this. Instead of saying M, right, the slope, what do we've learned this new thing for the slope, the derivative. Well, what graph is this? This is the slope graph, right? So at 1, at an x value of 1, what is this y value? Isn't f prime of 1 equal to 2? Haven't we been saying that all day long? That the y values on the f prime graph are what? The slope values on the f graph. And that's what we're wanting. We're wanting the tangent line on the f graph. So we need the point on the f graph, which is 1, 5, and we need the slope on the f graph. Well, the slope on the f graph is that y value right there, 2. So we put it right there, and we're done. That's all you do. But you got to understand. It's not hard. The problem's not hard to work out. You just got to understand, right? You got to understand the concept of what we're saying. We're saying we want the slope of the f graph. Well, they gave me the f prime graph. Those y values are the slope of the f graph. All right. Well, because point slope form, y equals m times x minus my x point plus my y point. So they told me they wanted the tangent line. They wanted the equation of the line at that point right there. So they gave, so again, how do I find the equation of the tangent line? You find the equation of the tangent line like you find any line. You just need an x and a y and a slope, right? Usually they're going to give you the x and the y, and then you get the slope, and it's going to be the derivative. That's what it's going to be. For us. I mean, back in Algebra 1, you found 2 points, you did a slope calculation. Not for us, right? We don't have 2 points, we have 1 point. What's the slope? Well, it's the f prime graph. The f prime graph is the derivative. Okay, 54, I tell you what, we'll talk about that one later, but I will tell you this, it's exactly what we talked about in class. Here's your 2 equations that they give you here, okay, and they talk about where the ball is thrown from and so forth. And so what height was the ball thrown? 74, because that's what this number is over here, the initial height. When you plug a 0 in for t, you get the height. What was the initial velocity? 38. That's this number right here, is the initial velocity. We know that from the equation. Was it thrown up or down? Up, because it's a positive slope. Okay. Was it increasing or decreasing at time 2? Where are you going to plug your 2 in? For which one? No. Because if you plug a 2 in here, all that tells you is the graph that the height is 7 or whatever. Well, how do you know it was on its way up at 7 or it's on its way down at 7? You don't. Where do you plug the 2? You plug it in here. You plug it in here. If the velocity comes out positive, what do you know? It's going up. If it comes out negative, it's going down. Okay? You plug the 2 into there. When did it reach its maximum height? What has to happen when the ball hits its maximum height? It has to stop. The slope's got to be 0. The velocity's got to be 0. So you take your velocity graph and you set it equal to 0. You get the time. That's the time that it was at its maximum height. But if they want to know, and that's what they ask, and then they want to know how high it was. So what do you do with that time? You plug it back into the height equation. That tells you the height. Okay? How long was it in the air? Set your height equation equal to 0. Because that's going to tell you threw it from here and it came up, and when the height is 0 is when it was back down on the ground. When the height is 0 is when it was back down on the ground. So you set that equation equal to 0, and that tells you the time that it hit the ground. And that tells you how long it's in the air. All you got to know is what these 2 equations tell you about the ball. The height of the ball, the velocity of the ball. And what do those things give you? And then it's just a matter of plugging in values and getting that. Okay, so here's the question for today. How do we find f prime of 1 if we're given a function f? How do we find f prime of 1 if given a function f? Well, we just did that problem on 47. If I give you, or not 47, but 42. If I give you an f graph, then how could you find f prime of 1? Well, how do you, that's what it's asking, but how do you do it? If I give you the f graph like this, right? And here's 1 right here. How do I find f prime of 1? Tangent line, God, struggling with that. Draw a tangent line and do rise over run, right? So if the f graph is given to you, or if you're given f as a graph, which is what we were in this section mostly today, then you could do rise over run. So that's one thing you'll have to do on our next quiz, I'm guessing. I'll give you an f graph, no equation, nothing like that, and you're going to have to sketch in a tangent line and estimate. Okay, but what if I give you an actual equation? Or what if I give you a table of values? Well, now we go back to what we learned the first day of class. right? And that was where we literally picked 2 points close together, right? Remember that? So if I want to do the f prime at 1, the slope at 1, the rate of change at 1, how about we pick 1 and 1.0001 and actually do a slope calculation right here. So if I give you an equation for f, then doesn't that give you a place to plug those numbers into, right? So you can use your calculator to actually plug those numbers in, okay? And then you can do like we did on that worksheet the very first day, and you can just plug those in. Now, you're going to, on the homework, they're going to say like zoom graphically. Well, here's what that means. To literally zoom in your window command, now let me show you, this is one of those that I gave you. You don't have to look, but let me just show you this example. This is a little document here. But if I wanted to find the slope at that black point right there, right? This window is actually zooming in. If I zoom in, look at the scale change here. If I actually zoom in, what happens eventually? It looks straight. In other words, what we're talking about here, this file is called local linearity. Local linearity. Well, what that means is if you look at a really small, that's what local means, a really small region right around this point. If you just look at a little tiny region right around this point, isn't the graph going to look straight? Like under a microscope, right? If you look at it under a microscope at this point, and that's what this is doing. Literally zooming in. Okay, so they may ask you on one of your homework problems to actually zoom in until the graph looks straight. And then ask you what your window is. You know, so you could give it your x min and max and your y min and max and tell it, you know, and just that's your answer. If they ask for that. If they say find a window where this graph looks like a straight line. That's what they're saying. Zoom in, zoom in, zoom in. What's that? Just go to your window settings. Yeah, you go to window, not window settings, you go to window and then zoom in is one of the choices. And then you zoom in. Usually it's good to trace to that point and get it right in the middle. Okay, so for example, if I was on my, let me go to a graph page here, and if I put in x squared, right, and I wanted to zoom in at, say at 2, so I would trace to 2, and I'd hit enter a couple. Oh, it puts a point there, which isn't a bad idea, actually. And then if I go menu, window, zoom in, it's going to ask me for my center. So you can use your trackpad and you can go like that, and then you go like that, and then you go like that. And that's why it's good. Do you hear what I said there on trace? If you hit trace and then 2 and hit enter, and then hit enter again, it'll lock a point there. It'll put that black point there. So if you trace to a point and then hit enter again after it traces to that point, it'll put that point there for you. So this is kind of nice. So now if I just zoom in, now that looks pretty straight, right? That looks pretty straight. So that's how you zoom in, right? And then I could just go to my window. If they wanted to know what my window is when I did that, then I could do that, right? And then I could just give them, I could just answer my x min and max. I don't know if it's going to ask you for that, but if it did, that's all they're talking about. Now, I don't have to zoom in, though, to pick 2 really close points, right? I could just go to my calculator screen. So if they wanted me to find f prime at 2, I could just go 2.00001 squared minus 2 squared, right? And then divided by, and then parentheses, 2.00001 minus 2, right? And there'd be my slope, right? So what do you guess on a parabola? What do you guess the slope is at 2? You suppose it's 4, right? So what I did there is what your book will call, when they talk about numerically zoom in, just numerically zoom in, you don't have to literally see a picture and zoom in, right? Zooming just basically means get 2 points really, really close. So if you want to do the slope at 2, just pick 2 and like 2.001 and do a slope calculation. So there's going to be a lot of that on the homework where they're going to say to estimate the slope by zooming. Well, Well, what they're saying is pick two really close points. So you will, look up here. You will be doing a lot of this today on today's homework. You'll be doing a lot of this right here, slope calculations. Okay? So instead of drawing tangent lines on graphs and doing rise over run, which is an okay way too, if all you have is a graph, that's the best you can do. But if you have an equation, you can actually plug in and get X and Y values. Okay, the last thing I would say would be a table. So if I wanted to do f prime of 2 on this table, what would you estimate? F prime of 2, what would you do? What do you think? How about pick those 2 points right there? Now, you might say it'd be smarter to pick 1.9 and 2.1, and I would say that would be okay too. I would say that would be fun. Okay, but I would say if you just did 6.41 minus 6 and 2.1 minus 2 and did that calculation, that's what they would be after. The idea is, in a table, you've only got certain values you can use. Pick the closest ones you can. Pick the closest ones you can, right? So it's not a big idea, but remember, we want to think about functions as equations, as graphs, as tables. We can be given functions in a lot of different various forms. Okay? All right, we spent a lot of time going over the homework because that's really, this idea of the derivative and f prime and f and that relationship is really important. What section 5 is about gives us a chance to catch our breath a little bit and really continue to process that and think about that. But it's also giving us a way to actually calculate some slopes, right? If we actually wanted to calculate some slope values, we can zoom in, we can pick really close points, we can do tangent lines and estimate that way, whatever. Okay, then tomorrow is when we're really going to get into it. Tomorrow is when we're really going to talk about these connections between f and f prime. Okay, and what is, if the f graph is doing this, what's the f prime graph doing, and then we'll bring in f double prime, and it gets kind of crazy. Okay. I would say if I had to predict right now, I would say, let's see, if this is Monday, Tuesday, Wednesday, Thursday, Monday, Tuesday, I would say next Tuesdays are quiz. Next Tuesdays are